Yeah, this is going to be a video about Fourier Transform and TIA Portal. In TIA Portal version 19 that we are working now, it's possible to calculate Fourier Transform by using the trace function. So we can have a little look at that. I have a setup here. So we can have a little look at how this can be done. So if we sit, this is probably okay for now. So here's a trace. It's a split screen. So what you have to do is a trace, and you have to make a, no, I'm going to stay here. This is the time plot of the noise. I'll just zoom a little in here. So there's a couple of signs here, and then there's some random noise on top of this. So what you have to do is you add a signal here. So this called we have a signal simulator, and this one has to be, for one odd reason or not, it has to execute on an interrupt. So this signal here is generated on every interrupt. I think we can see maybe the configuration here. It's a 5 millisecond cyclic interrupt, and I record every cycle here for the time diagram. So when you have added that, you can insert a new calculated signal, and then you can activate this function. You probably can't do it as it's running online. And you say you want an FFT analysis of the signal here. So that's the noise signal you see, and in the FFT, you select that. It doesn't show anything here, because what you have to do here is you have to stop the recording to have it to analyze. No data. We can try to stop and see what it does. Here, if it does a calculation, it did. And here it calculated, there is no DC part. It doesn't calculate the DC part as far as I can see. I've zoomed a little on this already. You get a wide range of frequency here. If we look at the signal we have here, that's where we set up the signal. We have 0.05 hertz here and 0.2 hertz, and then this random noise is just updated every, will this be 10th milliseconds or something like that. Here we get 005. There's a strong amplitude, and here is 02. I have a signal, and then there is some noise all the way here, and that's random noise. It should have pretty much the same frequency all over the spectrum. So that is the function. The thing here is it has to be, maybe we can have a look at it now. Yes. So what you do is you just add this FFT in the help file. There's probably some more argument you can have here too, and you can show the signal. So this is output of my signal simulator that's running on a 5 millisecond interrupt. So here you can analyze the signal. Here are two signs and some random noise. Now, that's one way of doing it. But programming here in high-level language, it is possible to make Fourier transform. You can make a fast Fourier transform, or this one, which is an incremental Fourier transform that has been running for some time now. And what it looks like here too is that my fundamental frequency is 0.01 hertz. It depends upon the number of samples I use here. And I'm sampling here every 20 milliseconds, and this continuous updating. And it seems like around the fifth, down here 4 to 5th, you see that's 0.001 times 4, so that will be 0.05, which is one of the frequencies I have. I have an amplitude about, what they say here is 11.5, and I have 8,000, but you have to add these two. It's somewhere in between here, because this fundamental frequency is not 0.01 exact. You see there are some envelopes too here. And if we look at the time diagram here, You can see it's oscillating. So here's the DC part. So it's oscillating around here 10 something. It depends on the noise too. So this is the DC part. And then there is something here, and the other one was 17 times this one. If we look at FFT again, which is around 0.02, there's an amplitude of 1500. That's what I have too. But also it's a spread test. So what I can do, I can block. I don't want to show this noise, but if I want to show the noise, I can double click here and say 0. And then I get all these noisy signals, and I should probably go on for a while down here. All the way, I think, yeah. But I'm not interested in noise, so I say, okay, the noise is low. What was the noise amplitude I had here? It's 1000. This is the maximum value, and there was 1000, and that's all over the spectrum, of course. Let's say everything below 1000 I don't want to see. So now these signals are popping out. These two signals that is in here. There is also, you want to see the frequency here. They are calculators. You had one on 17.20, so it's around here, but it is here. That's not too bad. For the 17th, and then we had some 0.05, which would be around here. So I don't get the center frequencies here exactly. Yes, so here you can have that was the amplitudes that we are looking at, the strength, and see it's in between here somewhere. And this is incremental, so it does the calculation rapidly. And here is for these 4096 sample, the processing time is around 2 milliseconds for this one. This just indicates it's active, and this is the sampling output. You can see once in a while there's a configuration error if you do configurations up here, so it doesn't match. I calculate 256 amplitudes. That is the maximum is 32,000. Here's the input signal as you enable and disable it. I'm not going to do that because it then restarts at 0 and try to increment it. And after 4096 calculations, then you are up to date here. So that will be 4096 times, what was it, 20 milliseconds then. It is possible also to, of course, change this to a lower rate. But this is not running on an interrupt. This is just running asynchronous in the background. But that's good enough for Fourier transform. You don't need it on an interrupt. But of course, you would get a more exact result here, because when you stop it, this Fourier algorithm probably try to find out or assess the fundamental frequency of the signal. And so on. And here is a 64-bit real calculation to have it. So that was fundamental. Here was just for the timing purposes. Now my machine has to think a little about what's going on here. So let me start. And the time diagram here, what you have to do, you have to stop it. So if you are recording here, I can just restart the recording. Yeah. Doing new recordings, but then if you see the Fourier diagram just disappears. Why they have opted to have this on? Let's see. I can't see the samples here, but you can see it down here too. I assume I can probably, maybe I can do something here. Well, probably this one, of course. Yeah, to get it back. So then you get one sample, and you can see the signal. And here you can also alter the amplitudes. I'm doing this incremental that has to do with lower signals and so on. So I could probably it's around 17. Here you see it's if it spreads out a little, because it's not running deterministic. This one, you know, you will lose the signal with 1,000. So just lower that. So this is just this is to get an idea here for what kind of frequencies is in the signal here. The important thing here is if this signal you have is not running on an interrupt, then it doesn't want to do any analysis. So if I now stop it again, it'd probably do a new calculation, I hope. Yes. See, it has another calculation here too, as this one has over here too. I haven't changed the signal or anything. So the idea here is to do filtering then of the signal, get rid of the noise, and it looks a little way I filter it. Maybe I'm losing a little too much of the signals, or I'm just decreasing the time constant for my filter, and it looks a little better over here. Get rid of the noise and at least some of the noise, most of the noise. So that was the noise signal. Yeah. So I'm running on a simulator CPU, not a real CPU, but it works pretty nice. Another thing here too, this algorithm for it's not that high level language in a PLC. It's not that difficult to program something like this. And you can also program a fast Fourier transform. That's a couple of 150 lines of code or something like this one here is probably 67, 70, 80, maybe 100. I don't know quite. But here the one issue was here to say, okay, for the fast Fourier transform, this is using fast Fourier transform. That's the reason why you have to stop it, because it needs a table. You probably adjust the table to a multiple of 2 or power of 2s and do a calculation. I don't know if they do padding or whatever they do in here, but here you can see also this has probably to do. You see the way I calculated to change 2 here. So here is probably, and it did a change 2. I haven't done anything whatsoever to the signals here. They are the same, running, generating on an interrupt, the signs and so on. You can see that if you just switch off the noise here too, and you can see what the sign is here. This is the signal they have. So I haven't done anything to it, but it depends. Maybe the simulator isn't it? I don't know. It changed, but you can see the same indication here on this discrete, and this one would now just settle down and get rid of this low frequency as this is running. So this would go down to 0 around here over time. So I switched off the noise too, didn't I? Yes, both the noise. And if I did a new recording here too, I don't know for how long I need to do this. I also have an interrupt in here running on 500 microseconds for some time keeping stuff. So it might be that the simulator of my PC is a little stressed here. Let's see, how much do we need here? Let it have a psych. No, probably okay. So if we go here, What kind of job do we do now? Yeah. It has some DC component here too, and it has an amplitude of 9,000 on the 4 here. It's a little spread out too. So the new calculation, what I've just recorded, one, let's say what is the fundamental frequency of the signal. But the DC part, I don't know why they don't display this. Maybe there is a line down here at 0. I don't know. I don't care too much here. Okay. Purpose of this video was to demonstrate a fast Fourier transform in TIA Portal version 19 with a trace. What you have to do is you have to have let's say a calculated signal, and you do fast Fourier calculation. You can also do a body plot and so on. There's other calculations you can do too in it. And then also I just demonstrated with just an incremental Fourier transform that's running pretty fast, executing in 2 milliseconds here on 4098 samples. And show how to calculate that too. And a program like that is not that program in high-level language. Is pretty easy to program, both fast Fourier transform and this is structured text, or SCL, and as Siemens call it. SCL is not structured text because Siemens, for one reason or not, they don't kind of adhere to the PLC open norm regarding structured text. That's probably why they don't call it structured text. But in SCL, it's really easy to write this, and then you can just make it asynchronous too. You don't have to run it in an interrupt like they do what you have to do with FFT in the trace function, because you can just run. Of course, it's a little more off for the calculation, and because it's not deterministic, for the sampling, but usually it evens out over time. So I had 20 millisecond sampling, maybe it was 21, as my cycle time is, I don't know what it is, but I think it's around a millisecond or something. There's quite a bit running on my CPU here. So it evens out. Maybe it's 22 millisecond, and then it's 18, and depends so on what the real time is, because I'm just calculating the sample type, but it would work. And this is not, let's say, an exact answer, but what you do is you get an indication of what kind of frequency components do you have in the signal. And what I do too is that I can suppress these small signals, as I demonstrated with the noise, to say, okay, signals with a small amplitude, I'm not interested in those. I want these signals with a significant amplitude. But of course, just looking at the recording I have in the time plot, I can pretty much assess what kind of frequency do I have in the signals I generate. But this is then again just for demonstration purposes.